In this video, we'll explore the concept of independence. We've been exploring conditional probability, that is, the recalculation of the plausibility of an event A in light of information about another event B. But sometimes information about B doesn't change our understanding about A. That is, these events might be independent. Consider an example. Suppose I have 6 pairs of shoes, 4 blue and 2 red. Thus I have 12 shoes total. Then suppose I pick one shoe at random and let B be the event that it's blue and L be the event that it goes on the left foot. Then since 8 of the 12 shoes are blue, the probability that I get a blue shoe is 2/3. Now suppose I don't tell you what shoe I got, but I do say that it goes on the left foot. This information shrinks our sample space down to 6 left foot shoes. Among these, 4 are blue. Thus the probability that I got a blue shoe given that it goes on the left foot is 2/3. Stepping back, notice that the unconditional probability that the shoe is blue is equal to the conditional probability that it's blue, given that it goes on the left foot. In other words, information about which foot the shoe goes on did not change our understanding about its color. That is, shoe color and shoe foot are independent. In general, two events A and B are independent if and only if the conditional probability of A given B is equal to the unconditional probability of A alone. That is, if information about B doesn't change our understanding of A. An equivalent definition states that two events A and B are independent if and only if the probability of their intersection is equal to the product of their probabilities. Before applying these two definitions of independence, let's convince ourselves that they are equivalent. In general, to prove that two definitions are equivalent, we have to show that each definition guarantees or implies the other. Let's start by showing that the first definition guarantees the second. That is, let's assume that the conditional probability of A given B equals the probability of A. And let's then prove that the probability of the intersection equals the product of the probabilities. In this case, we've observed before that by rearranging the definition of conditional probability, we can write the probability of A and B as the product of probability of A given B and the probability of B. But by our assumption here, the conditional probability of A simply equals the unconditional probability. Hence, we've shown that the first definition of independence guarantees the second. Next, let's show that the second definition of independence guarantees the first. That is, let's assume that the probability of A and B equals PA times PB, and prove that the probability of A given B equals the probability of A. To begin, by the definition of conditional probability, the probability of A given B equals the probability of A and B divided by the probability of B. But by our assumption here, the probability of A and B equals PA times PB. Notice then that the probability of B in the numerator and denominator cancel out, establishing that the second definition of independence guarantees the first. Now that we've established some theoretical results, let's apply them. Let's first consider how we can use these definitions to identify whether two events are independent or dependent. For example, suppose a recent political poll estimates that a certain senator has an overall approval rating of 40%, but a 70% approval rating among Green Party members. Does this information imply that the senator's approval is independent of or dependent on political party? Intuitively, these events are dependent. If you tell me that somebody is a Green Party member, it changes my assessment of whether or not they approve of the senator. We can confirm this hunch with some math. First, the given information suggests that the overall probability of approval is 0.4, and the conditional probability of approval given that somebody is a Green Party member jumps to 0.7. Since these calculations are unequal, or the information about Green Party membership impacts the chance of approval, we can say that approval is dependent on one's party affiliation. Next, suppose the poll suggests that the senator has an overall approval rating of 40% and a 40% approval rating among 18 to 29-year-olds. Does this information imply that the senator's approval is independent of or dependent on age group? Intuitively, these events are independent. If you tell me that somebody is an 18 to 29-year-old, it doesn't change my assessment of their approval of the senator. Again, we can confirm this hunch with some math. First, the unconditional probability of approval and the conditional probability of approval, given that somebody's 18 to 29 years old, are both 0.4. Since these calculations are equal, or the information about age did not impact approval, we can say that approval is independent of age. Finally, let's use our definition of independence to make some probability calculations. Suppose that roughly 25% of Mac students fall into each group: first year, sophomores, juniors, and seniors. Further, suppose that roughly 10% of Mac students are left-handed. It's pretty reasonable to assume that handedness and year in school are independent. Mainly, somebody's year in school doesn't change their likelihood of being left-handed. In this case, then, what's the probability that a randomly selected student is a left-handed senior? By the assumption of independence, the probability that a student is both left-handed and a senior is the product of the individual probabilities. Plugging in the given information, there's a 10% chance that a student is left-handed and a 25% chance that they're a senior, for a final probability of 0.025. In conclusion, then, 2.5%, or 10% of 25% of Mac students, are left-handed seniors.